All right, welcome students. And today we're going to be talking about solutions and kind of discussing what solutions are. And this is basically an introduction to that, just a couple brief concepts. Tomorrow or the next presentation that we're going to have, we'll get into kind of more how do you calculate strengths of solutions, and sometimes we refer to something as diluted or concentrated, and we'll figure out kind of how to calculate how concentrated or how diluted something is. But that's for a later date. So let's answer the question, what is a solution? Here's the official definition, and this is also in your definition sheet. It's a homogeneous mixture of variable composition. If you remember, a homogeneous mixture is one that looks the same. You can't discern one region from another. So whatever the two substances or three substances that are together, you can't tell them apart. And there are two basic parts to any solution. And if you remember nothing else in this section, this would be a good idea to remember. The first part is called the solvent, and it's the major substance in a solution. If you want to call this the substance being dissolved, or excuse me, not substance being dissolved, the substance doing the dissolving, you could refer to it that way. And you may want to write down next to this, when we're talking about liquids, water is the universal solvent, or is referred to as the universal solvent. So the majority of things we talk about in here that are solutions and that are liquids, the solvent will be water. That's not always the case, but it is quite often in this level of chemistry. The other part to a solution is the solute. And so those are the two key ones to know. And the solute is the substance that is being dissolved. And generally speaking, you only have one solvent, but you can have more than one solute. Now, for most of the examples that we will use, for example, let's say salt water, you only have one solvent and solute, but it is possible to have more than one solute. You can mix several things together. So those are your two major things. And those will be things that we will be repeating, and you would be expected to know what is what. So when we say the word solvent, you would know what that is. Or we say the word solute, you would know what that is. That will be super important, as you show up to class tomorrow. All right. What are the different types of solutions? We're just going to go through this real quickly. Most solutions are liquid solutions. Not all of them, though. And there's a couple things about liquid solutions that we just want to keep in mind. They're the most common, liquids are the most common type of solvent. Again, you can dissolve like solids into a liquid. You can even dissolve a gas into a liquid. A good example of that would be soda, where you have carbon dioxide dissolved into water to give it kind of the fizzy taste that we have. And you even visibly see those bubbles. Couple things with liquid solutions. You have miscible solutions, which are a big fancy word there, simply means that you have two or more liquids that are mutually soluble in one another. So you can pour two liquids together, they dissolve in one another. That's easy to see. You could do, I don't know, I suppose water and orange juice, or you could do orange juice and milk. I don't know why you would do that, but they would be mutually soluble in one another. And again, really because most of them are made up of you could do vinegar, I suppose, and water. There's a number of different things you could do. Well, we'll just stick with that as examples. Another one is immiscible solutions, and immiscible solutions are two or more liquids that are not mutually soluble in one another. And let's deal with this word soluble right away. So off to the side, you may want to jot a note to yourself. What does it mean, that word soluble? Because we'll be using it a lot this chapter. Soluble means it has the ability to be dissolved. Okay, that's simply what that means, the ability to be dissolved in something. And so something that is not mutually soluble or immiscible would be like oil and water. If you put oil and water together, they don't mix. Oil does not dissolve in water. And we'll talk about the reasoning behind that a little bit later. But that would be one quick thing. Of course, you have solid solutions. Probably your best example of that would be like alloys of metal, where you have a couple different metals mixed together like stainless steel is a mixture of iron, mostly iron in there. I believe carbon and zinc is sticking on the top of my head. I'm not positive about that though. Gaseous solutions, an example would be the air around us, and you have a mixture of several different gases, nitrogen being the solvent because it's the majority substance, and then you have like oxygen would be one of these solutes, it's the major solute, and then you would have things like carbon dioxide and argon, which are other solutes as well. So those would be different types of solutions. And gases can act as solvents only with other gases. That's the only time they can do that. All right, the dissolving process, real quickly, basically involves two steps, and then I'm going to kind of put them up here real quickly and then allow you to see a quick video because the video does a better job than me explaining it here. And that it involves two steps, and one is solvation, and that's the process in which solvent particles surround and interact, and by interact, there's kind of a sort of bonding process that goes on with that, in that you have the positive ends, let's say, of water, because it's a polar molecule, will interact with, let's say, positive ends of, or negative ends of something else. So you have opposites attract. And then dissociation is the breakup of solvent and solute particles from their own kind. And so we're going to watch a video kind of how this goes about here and kind of take a quick look at that.
Sodium chloride crystals are held together by attractive forces between the positively charged sodium and negatively charged chloride ions. When a crystal of sodium chloride is placed into water, the hydrogen ends of polar water molecules attract the negatively charged chloride ions and gradually surround them.
Okay, I'm going to pause the video right here. So that you can kind of take a look what's happening here. You have this big molecule of sodium chloride, and it's actually made up of multiple formula units or molecules of sodium chloride, and the green there, I believe, is the chlorine, and the white would be the sodium in this case. And then you have all those little water molecules around. And the size differential is just to show that there is a size differential in real life. And so you see you have a lot more water molecules than you do salt. And so on a molecular level, what's happening is, if you see the, let me see if I can get my laser pointer here. Nope, I can't. But if you look over there in the upper right there where the water molecules are attracting the green thing, if you see they're surrounding the little white parts, okay, that's the hydrogens, the small little white balls on the waters. Those are the hydrogens, and they have a positive polar, if you remember as a polar molecule, those are the positive end. The red part, that's oxygen, has a negative end, and the positive parts are surrounding the green negative sodium chloride ion. And we're going to see what, and this is how it breaks up what goes on. So when you see that salt crystal dissolving, what's really going on. So we'll continue to play this here.
Likewise, the oxygen ends of water molecules are attracted to and surround the positively charged sodium ions. The hydrated ions drift away into the solution, allowing new water molecules to surround newly exposed ions. Gradually, the entire crystal dissociates into solution.
Okay, so you saw there kind of the process of dissociation there real quickly, how you have oppositely charged particles and different molecules surround and cause breakup. And we'll talk more about that a little bit later, and I'll kind of draw some more examples on the board when we get back to it. But that's just to give you kind of a familiarity of what's going on actually on the molecular level. Okay. Let's take a look at some rules for solutions and solution equilibria. The first rule is like dissolves like rule. And this is basically, why do things like oil and water not mix? And other items do. What is it kind of that governs that? Well, simply the like dissolves like is the general rule of thumb. And basically what this means is that polar substances will dissolve other polar substances. And nonpolar will dissolve other nonpolar. And in the case of oil and water, oil is nonpolar and water is polar, and so they don't mix. Okay, and part of the reason behind that is kind of what you just saw in the video. You had two polar substances, salt and water, and I put them together. They're both polar, and so the positive ends of salt will attract to the negative ends of water, and the negative ends of salt will attract to the positive ends of water, and that's what helps dissolve it and pull it apart. And in something like oil that's nonpolar and doesn't have those positive or negative ends in the same sense, then it won't do that. Solution equilibria. Okay, we're just going to throw out three quick terms here. Unsaturated, saturated, and supersaturated. And basically these refer to solutions that at particular temperatures, so you have a set temperature, and unsaturated is when that solution has less than the maximum amount of solute. In other words, you can add more to it and it still dissolve. Saturated is when it contains the maximum amount of solute. No more can be dissolved in it at that particular temperature. Temperature is a key factor, and we're going to talk about that in just a minute. And then there's supersaturated, which is a solution that contains more than the maximum amount of solute. You may ask, well, how can you get more than the maximum? Real simply, the way to do this usually is you heat the solution up, you change the temperature, dissolve more solution, and then you cool it down, and it will remain dissolved as you cool it down unless you do something to it. And sometimes they call this seeding. You can a good example would be rock candy. So if you heat the solution up, you put a lot of sugar in there, a lot of sugar dissolves, and then you cool it down, to room temperature, and then you add a little bit more sugar on like a string or something like that can disturb, and the extra sugar begins to precipitate out, okay, or become a solid, and you can get something like rock candy or whatever. All right, quickly we're going to move through factors that affect solutions, and there's kind of two different categories. One, factors that affect the rate at which something dissolves, and there's two things basically here, and these are going to be super important for you to know. And one is the inherent solubility, which is just a substance's natural ability to dissolve. How well can it actually dissolve? And this is something that you really can't change yourself. But there is something we can manipulate, and that is the second thing that we can affect. How fast can something dissolve? The frequency of collisions between solvent and solute particles. For example, stirring, okay, is one of those things we can do to change the number of collisions. The more I stir, the more kinetic energy I'm adding. And the more kinetic energy I add, the more collisions I'm going to have, which causes the speed at which it dissolves to go faster. Temperature is another thing. If I increase my temperature, there's going to be more collisions between solvent and solute particles. Why? Because by increasing temperature, I've added energy. That's the key. If I decrease the temperature, then it's going to take more time. And sometimes, to be honest with you, we work against ourselves. For example, if you're making lemonade, we put ice cubes in to make the lemonade cold, and then we stir it to dissolve, the Country Time lemonade, in there. And so we stir it to make the collisions more, but we would put the temperature down because we want the drink cold. And so sometimes we kind of work against ourselves here unknowingly. And the last one is surface area, and this is just how much surface area is exposed. If you think of you're putting sugar, granulated sugar in, like from your jar at home, and you put the same amount of sugar, but it's in a sugar cube, well, the granulated sugar is going to dissolve faster simply because more of it's exposed to the water. In a sugar cube, the only part of the sugar that's exposed is that which is on the outside. All of the sugar that's on the inside of the cube is not even touching the water, so it can't dissolve. So that's kind of some basic factors that affect solutions. And we'll probably revisit this in the next video and also talk about some other factors, not only that affect the rate, but can affect some other things as well. So we are done for today.